Here we are. Good morning, guys. Yeah, lads and ladies, welcome back to Calc 1. Today we have a really exciting section to cover, so I'm stoked to get in here and start working with you guys. I'm going to go ahead and turn on the screen share and we can get started. Oh, what is this? Oh, QCam isn't up. Okay. There we go. All right. There she is. Let's do it. So I know with spring break next week, it's tempting to sort of disconnect a little bit right now, but it's very important that you don't do that. It's very important that you kind of stay actively engaged, because things this week, the material we're covering is a little bit challenging, and it's also hugely important. So I'm very excited to go through this with all of you. And I just ask that you continue to show this class the respect you've been showing it. Don't hesitate to ask for help if you need it, because where we're going this week is here, right? Summary of curve sketching, and this is actually a really big deal. So all throughout your algebra classes and throughout this class, I'm sure you've noticed how important graphs are, right? The ability to sketch a reasonable graph of a function is probably the single most important skill coming into calculus, and it's one of those skills that we need to perfect and improve throughout calculus. Section 4.5, which is the section we're going to start on today, teaches us how to draw really, really good graphs. And the good news is it doesn't mean just plotting more and more points. We know we can get a good graph, for example, of this function just by plugging in a shitload of x values, right? You plug in a shitload of x values, you make a really big table, you connect all the points with a curve, and you get a reasonable graph. That's what computer programs do, right? Like if I ask Desmos to graph this, that's precisely what Desmos is doing. It's going to do thousands and thousands of little computations to come up with a big, big, big table, and it's going to put all those points on the plane, and boom, there's your graph. Human beings, though, we don't like to build tables with thousands and thousands of entries by hand because we have these little hands and they get tired and it's not fun. What we can do instead is run through a really nice procedure. And that procedure involves, among other things, finding where your function is increasing and decreasing, finding where your function is concave up and concave down, finding where you have mins, maxes, inflection points, asymptotes, all of those things, and then putting all of those pictures together with a few points, not a bunch of points, but a few points to get a really sweet looking graph. That's precisely what we're going to do today. So I'm going to run you through this sort of algorithm. And you see here it's quite long, right? It goes all the way out to H, steps A through H, to get a beautiful graph of relatively complicated functions. Unfortunately, this still takes a little while, right? It's not super fast. So we're not going to get to do a bunch of examples, but we will get to do some examples, and I'll try to do as many as we possibly can. I noticed that a relatively large number of folks asked for extensions on the last homework, and that's understandable because that was a fairly long homework set. I've already gone in and granted those. Please make sure you finish last week's homework before starting on this week's homework. That is important. All of those skills come back here in a big way. So let me come over here. We can get started properly. And this is MAC2311, section 002. It is a lecture. And today is the 1st of March, 2021. Today, we're going to do curve sketching. Which is section 4.5. Oh, come on. Come on. Come on. There it is. All right. I also, if there are problems from the previous homework set, we can maybe do one of those, but I want to put them towards the end. So If there are homework problems from the last set that you're stuck on, you can type those in chat. And after I get through a few examples, kind of helping us see what 4.5 is all about, we'll go ahead and look at some extra homework problems. So first, let me just go ahead and write down this algorithm. So to sketch a good graph of the function y equals f of x, we find, and I'll label it like they do. First, the domain. Now, a few people have come to me in office hours asking some questions about domains, which are perfectly reasonable. The way I like to tell people how to find a domain is to look out for these things I call domain red flags. So red flags for finding domains. That's fine. Okay, sorry about this. Give me just 1 second. Close Outlook. All right. Red flags for finding domains. Things you need to look out for. The downstairs bottom of a fraction can't be 0. So if you have variable stuff in the denominator, that's a red flag. If you have x's or t's or whatever your variable is, anything containing those downstairs, you need to make sure that those pieces are not 0. The other thing you need to make sure is that stuff, even roots. Need to be greater than or equal to 0, right? So variables under a square root or variables under a 4th root, those all need to be greater than or equal to 0. Any chunk of things that is under a square root or a 4th root or a 6th root needs to be greater than or equal to 0. And then the third one is that stuff inside logs, inside natural log or any other base log, must be strictly greater than 0. These are the 3 kind of things you need to watch out for if you're looking for the domain of a function. The second thing we want to look for is intercepts, x-intercepts, y-intercepts. To find x-intercepts, let's do y-intercepts first, they're easier. You just plug x equals 0. Right, the y-axis is all the points in the plane whose x-coordinate is 0. So if you want to find the y-intercept for any function out there, you just plug in x equals 0. Not every function has a y-intercept, right? Of course, if 0 isn't in the domain of your function, then you cannot plug in x equals 0. And that's fine. Not every function has to have a y-intercept. To find x-intercepts, we find these. These are found by solving the equation f of x equals 0. And if your function happens to have like a top and a bottom, like your function is a big fraction, usually you can get away with just setting the top equal to 0. But that's because that's equivalent to setting the whole thing equal to 0. The next thing you're going to look for is any symmetry that might help you. Is f even, odd, or neither? Remember, an even function satisfies f of negative x is equal to f of x. And an odd function satisfies f of negative x is equal to negative f of x. So to detect these symmetries, you replace x by f of x. You replace x by negative x and try to simplify. If you're able to simplify f of negative x to regular old f of x, then you have an even function. And if you're able to simplify f of negative x to negative f of x, you have an odd function. And each of these come with their own symmetry. This guy, if you have this, then you'll have y-axis symmetry. And if you have this, you'll have origin symmetry. And these are all terms you should be familiar with from pre-calculus, but I'll try to look at an example of each. Oh, and periodicity, right? So here, and then also is f of x periodic? If so, what is the period? All right, we all remember what periodic functions are, things like sine and cosine, tangent. All the trig functions are periodic with period 2 pi, meaning they repeat every 2 pi. So if you have a periodic function, you find the period, sketch one period of that function, and that tells you everything you need to know. Okay, continuing. Asymptotes, right? Find vertical asymptotes, find horizontal asymptotes. All of this is still algebra stuff. So we have to find vertical asymptotes. These are places where f of x blows up to plus or minus infinity, and horizontal asymptotes to find these, we calculate the limit as x goes to positive infinity of f of x, and we calculate the limit as x goes to negative infinity of f of x. And that's what horizontal asymptotes are. If either of these things come out to be a finite number, that means that your function has that finite number as a horizontal asymptote. And if there are any x values where your function blows up to plus or minus infinity, that means you have a vertical asymptote at that x value. So this is when I teach my kids in college algebra how to graph rational functions. This is exactly what I tell them to do, right? This is the whole game. But you guys are not algebra students. You guys are calculus students. Here, I'll hold this for a second. So the big new stuff for us is going to be finding where is your function increasing and decreasing? Do you have any mins and maxes? Where is your function concave up and concave down? Do you have any inflection points? Once you have these things together with those things, you will be ready to draw a really nice graph. And this might look like it takes forever, but it really doesn't. It does take a little while, but it goes faster than it appears to from this. I'm going to turn the page in about 5 seconds. Okay. Let's keep this in the order your textbook does it. Intervals of increase and decrease, local mins and maxes. What are we on? These are like, where is f prime positive? And if intervals of decrease, these will be places where, to answer this, we need to know where is f prime negative. F is mins and maxes. And we can find these guys by making our number line. This really comes together. So places where f prime of x changes sign. And really, these two, you get them together. These both come from the number line for f prime. An alternate approach to the mins and maxes thing, you can use the second derivative test. And we haven't gotten to talk about that yet, so I'm going to show you what that is right now. It's not a complicated thing, but as soon as we finish making this list here, I'll show you that. And then the last sort of thing we need to do is find where we're concave up and concave down. So intervals where f of x is concave up or concave down. And that's really it. This all comes from the number line for f double prime. And they list an extra one here. They say just sketch the curve. So why not sketch the curve? Maybe plot a few extra points. Having gone through this whole procedure, you found your x-intercepts, your y-intercepts, all your mins and maxes, all your inflection points, all that good stuff. You should have plenty of points. But sometimes you'll find a lot of functions don't have a lot of these features. And so when you get to this last step, you may want to make a little table and find a few extra points. But that is it. That is it. So real quick, what is the second derivative test? The first derivative test, remember, is that thing with the number line for f prime, right? You make a number line for f prime, and if you go from increasing to decreasing at a point, that means you found a max. And if you go from decreasing to increasing at a point, that means you found a min. The second derivative test is a way of kind of getting the min and max information without making the number line for f prime. It's not necessarily relevant to this procedure because you need to make the number line for f prime to go through this procedure, but it's a theorem in the textbook, so I wanted to show it to you really quickly. This just says if c is a critical number for f of x, then I should say, and f prime prime of x is continuous at x equals c, then if f double prime of c is positive, so you have a horizontal tangent line, and you're concave up at that point, that means this has to be a local min. So f of x has a local min at x equals c. And if f prime prime of c is negative, that means f of x has a local max at x equals c. The idea here is that if you have a critical number, that means that this is like a horizontal tangent line or something like that. So here's your horizontal tangent line. If this is the graph of f that we're looking at right here, this is the graph of the original function. I'll call this number right here c. This function is concave down right here, right? So f double primed would be negative. And that corresponds to what we're saying here, yeah? If f double prime is negative, less than 0, then f has a local max there. So if you have a horizontal tangent line at some number, and your second derivative is negative there, that means that you must have been concave down, which means your graph had to have been shaped like this when you had your horizontal tangent line. And that means that that has to be a local max. Similarly over here, I'll call this, I'll call this B. A horizontal tangent line here also. But here f is concave up, which means f prime prime of B is positive. So if you're concave up and you have a horizontal tangent line, then that has to be a local min. Okay. Like I said, the second derivative test is not super duper relevant for what we're talking about today, but it is a theorem from the textbook that I wanted to make sure you saw. There's a kind of more important version of this that you're going to see in Calc 3. When you're talking about functions of more variables, when your graphs have like 3 and 4 dimensions, the first derivative test stuff doesn't really work. You can't talk about going from increasing to decreasing because it kind of depends upon the path you're taking. So this is really the only way to attack these sort of questions in the higher dimensional setting. That's the main reason we show it to you here. So having done all of this, let's take a look at an example. No, where are we here? We can run through that one. There's actually, I have another example that I like more than this, but we'll do this one first. All right, so we're going to use those guidelines. I'll write this down. Sketch y equals 2x squared divided by x squared minus 1. Okay, first we're going to find the domain. So what sort of domain red flags does this function have? What sort of stuff should we watch out for?
X can't equal 1.
It's true that 1 is a problem, but it's not the only problem. So we want to kind of, you're correct. But if we follow the guidelines exactly, they say, right, we got to watch out for any variable stuff in the denominator. That's not allowed to be 0. And I know that's where you're getting that. But if I set up this equation and solve it, I'm actually going to find 2 numbers that are problematic.
Plus or minus 1.
Yeah, exactly. We can do this by factoring or by adding over and taking square roots. Either way is fine. So you get here the 2 solutions, x equals 1 and x equals -1, making the bottom 0. So x cannot be either of these. And our domain is -∞ infinity to -1, union with -1 to 1, union with 1 to infinity. The second thing we want to look for are intercepts. The y-intercept always comes from plugging in x equals 0. So if I take 0 and I plug it in here, I get 2 times 0 squared divided by 0 squared minus 1, which is 0 over -1, which is 0. So the y-intercept is the point 0, 0. And x-intercepts, we set the whole thing equal to 0. And the first step towards solving this equation would be to maybe multiply over by this whole denominator. So I'd get 2x squared equals 0 times x squared minus 1. But that's the same as saying 2x squared equals 0, which is the same as saying x squared equals 0. And the only way that happens is if x is equal to 0 itself. So this y-intercept is also our only x-intercept. It's possible that there were other ones, right? It's possible if this top was 0 at other places, we would only discover that now. So it's still worth going through this as its separate thing. The next thing we're going to look for is symmetry. Here, f of negative x, and this is the graph y equals f of x is this thing. To find our symmetries, remember what we do is we swap in negative x for x and see what happens, see if we can simplify it to either the original or the negative of the original. So here I'll have 2 times negative x squared divided by negative x squared minus 1. That's the same as, well, what is the square of negative x? What happens if I square negative x?
Become positive.
Yeah, this just becomes 2x squared again. And downstairs, this becomes x squared again. And what is this?
F of
The
x.
same.
Yeah, that's the original function. So what have we seen? F of negative x is the same as f of x. So this tells me that f of x is an even function. Therefore, its graph is symmetric about the y-axis. Okay. This definitely is not a periodic function though, right? Like this thing has no trig functions in it. There's nothing in here that would make this periodic. So we don't have to worry about periodicity, but we do have that y-axis symmetry. Our next thing to look for are asymptotes. So first, maybe vertical asymptotes. Looking at the kind of algebra shape here, f of x is 2x squared over x squared minus 1. Can anybody think of a place where this function might blow up to infinity or negative infinity? Anywhere this function might become undefined. in a kind of fantastic way. What is, if I take a finite number and I divide it by 0, what do I get? Like what's 1 over 0 or 2 over 0?
0.
If I take 0 and
Undefined.
divide it by something, then I get 0. But if I take something and I divide it by 0, that's going to be like plus infinity. So this function is going to blow up at exactly the numbers -1 and 1. Right, so for rational functions, for ratios of polynomials, you'll get vertical asymptotes by setting the bottom to 0. So this goes to infinity as x goes to plus or minus 1. So we have vertical asymptotes at 2 spots. X equals -1 and x equals +1. Kind of your picture here, the thing in your head should be 1 over x, right? We all know that 1 over x blows up at 0, where his bottom goes to 0. So if you have a fraction, a rational function, then to find vertical asymptotes, you do the same thing you do to find the domain. You set the bottom to 0. And since each of these factors is 0 at 1 and at -1, we know those will be the places where this thing blows up to infinity. So this guy does blow up to infinity, and he does that as x gets closer and closer to 1, or as x gets closer and closer to -1. Horizontal asymptotes. It's possible to have 2 different horizontal asymptotes, but this function is symmetric about the y-axis. All right, so by our symmetry, what happens on the left will be the same as what happens on the right. Lim x to -infinity f of x will be the same as lim x to +infinity of f of x. And here, the limit as x goes to +infinity of f of x is lim x to infinity 2x squared over x squared minus 1. And we remember the trick for these. Limits at infinity of rational functions, we divide top and bottom by the largest power. So if I divide top and bottom by x squared, I'll get lim x to infinity 2 divided by 1 minus 1 over x squared. I just divided the top by x squared, and I divided the bottom by x squared. I divide every single term by x squared. Now this piece, 1 over x squared, is going to go to 0. So this is going to be 2 over 1 minus 0, or 2. So my horizontal asymptote is going to come over here. My horizontal asymptote is only one of them, and it's the line y equals 2. This is all the algebra stuff. Now we're ready to start on the calculus stuff. Questions on any of these things? Some cheat codes for this stuff. Symmetry. If all the powers of x that show up in your function are even, you have no odd powers of x, then automatically you can tell you're dealing with an even function. So we could have said right away, okay, every time an x shows up here, it shows up squared. That means this is automatically going to be an even function. cheat code for vertical asymptotes, you get them with the domain. Set the bottom equal to 0, those will be your vertical asymptotes. And we already did that back when we found the domain. So really we weren't doing anything fresh here. Okay, now here comes the big stuff. Intervals of increase and decrease. And I'm also going to do F, which was mins and maxes. We do these together with the number line. So intervals of increase and decrease. That's my shorthand here, inc and dec. And mins and maxes. These all come from the first derivative, which is the derivative of 2x squared over x squared minus 1. And we should really use the quotient rule here. This is a place where the quotient rule is appropriate. So that's the bottom times the derivative of the top. The derivative of 2x squared is 4x minus the top times the derivative of the bottom. The derivative of x squared minus 1 is 2x minus 0. All over the bottom squared. And we can simplify this. I can distribute my 4x here, and I'll get 4x cubed minus 4x. I can distribute the negative 2x squared here, and I'll get minus 4x cubed. And then downstairs, I still have x squared minus 1 squared. And there's no reason to FOIL out the bottom. Just leave the bottom like that. The 4x cubes cancel, and we get negative 4x over x squared minus 1 squared. Still my critical numbers. Remember, the game here is to make the number line for f prime. That's what we're going to do. That's how you always do this. That number line, we start by finding our critical numbers, and then we plot those on a number line. What are the critical numbers here? These are places where f prime of x is equal to 0, or f prime of x is undefined.
0 plus 1 minus 1.
Yep. And technically, plus and minus 1 are not critical numbers, right? Because they're not in the domain of the original. But I'm going to put them on my number line anyway. So I don't expect to find mins or maxes or anything special like that at plus or minus 1. But because they make f primed undefined, they're still special for the problem. We still want to continue to think about them. So this will be my number line for f primed. We should label it as such so our reader can tell what the hell is going on. Now I need to take a test point from each one of these regions. Over here to the left of -1, I could test x equals -2. F primed of -2, all I really care about is whether it's positive or negative. That's going to be -4 times -2, which is +8, divided by -2 squared, which is 4, minus 1, which is 3, all squared, which is 9. So in particular, this is positive. between -1 and 0, I can test something. Between 0 and 1, I can test something. And then to the right of 1, I can test something. But I'll also be able to exploit symmetry eventually here. I'll show you what I mean. So I can test x equals -1/2 here. If I plug in -1/2 to f primed, -4 times -1/2 is +2. And downstairs I would have -1/2 squared, that's +1/4. +1/4 minus 1 is -3/4. -3/4 squared is 9/16. And again, I don't care about simplifying this. I just want to know, is it positive or is it negative? This is positive. To the right of 0, I can test x equals 1/2. F primed of +1/2 is -4 times +1/2. That's -2. And then downstairs here, -1/2 squared is +1/2. Sorry, it's +1/4. +1/4 minus 1 is -3/4. -3/4 squared is 9/16. And this is definitely a negative number, right? You take -2 and divide it by a positive number, you're going to get a negative number. So this will be negative. And off to the right of +1 here, we could test x equals 2. F primed of 2 is -4 times 2, which is -8. And downstairs here, you'll have 2 squared is 4, minus 1 is 3, 3 squared is 9. So this is -8, and it's negative here. Like I said, you can also think about this as a symmetry thing. If you know you're increasing over here, and you picture what happens if you take a graph that's increasing to the left of 0 and reflect it over the line y equals 0, or x equals 0, reflect it over the y-axis, you get something that's decreasing on the other side. I'll let you think about how we could have used the symmetry to make this go a little bit faster. But this thing with test points, this always works. So if you're uncertain or if you want to check your work, say you think due to symmetry that these being positive would make these negative. If you want to check that, you could test the points. And you should run through enough of these that you get confident with whatever system you choose to use. Before I move on and start making conclusions about this number line, are there any questions about where these things came from? Or this derivative?
Or where did the
I'm sorry, Robert, could you say that?
Yeah, where did the -1 and 1 come from?
Those were places where f primed is undefined, right? Because the bottom here will be 0 if x squared minus 1 is equal to 0. And that happens at plus and minus 1. So if we set the top to 0, -4x equals 0, if and only if x is 0. When we set the bottom to 0, x squared minus 1 squared is equal to 0. That gives us plus and minus 1. Okay. Is there a min or a max at -1?
No.
No, there's not, because we're increasing here and we're increasing here. Is there a min or a max at 0?
Yes.
Yeah, what's going on there? Is it a min or a max?
Max.
Good. Because I'm increasing to the left of 0, right? This function here, I'll draw them in down here, our little arrows. So we're increasing, increasing, decreasing, decreasing. So the only place where we went from increasing to decreasing is at 0, right? So we have a local max there. We're increasing on both sides of -1. We're decreasing on both sides of +1. So there's no mins or maxes there, but we definitely have a max here. And we know that there shouldn't be a min or a max at -1. Why? Remind me.
It's not a critical point.
Good. -1 isn't a critical number. Why? F primed is undefined there.
Because it has the like vertical asymptotes.
Very good. We know that f of x has a vertical asymptote at -1. In other words, we know -1 is not actually in the domain of f. Remember, critical numbers are places where this happens that are also in the domain of the original. All right. So yeah, we knew we had a vertical asymptote here. We knew we had a vertical asymptote here. We didn't expect to find anything fun there. But we're just being careful because I want to know, am I increasing or decreasing in each of these regions? Okay, so that's parts E and F done. We now know where we're increasing. F x is increasing on -∞ to -1, unioned with -1 to 0, and f of x is decreasing on 0 to 1, unioned with 1 to infinity. And f of x has a local max at x equals 0. And what is that max value? Well, it's the y value on the graph there, f of 0, which we found earlier, but we can double check. This is what we would normally have to do anyway. Plug 0 back into the original, and you get 0 over -1, which is 0. So the local max occurs at x equals 0, and the max value is 0. Is everybody with me so far? All right, we're almost ready to sketch our graph. The last thing we need to do is find out where we're concave up and where we're concave down. To do that, okay, let me do this. So I'm going to zoom out a little bit and I'll hold here for a second in case anybody needs to write any little pieces. While we're doing that, I'm going to refill my cup. Oh. Okay. What we need to do is figure out where f is concave up and where f is concave down. So our very last step here. And we're also going to find any inflection points. Inflection points are places where that concavity changes. F double primed is the derivative of f primed. Take f primed and differentiate it. F primed was -4x over x squared minus 1 quantity squared. Oh, okay, let's focus. Focus. Okay. So I need to differentiate this, which is f primed, in order to get f double primed. There's a few ways you could do this. I think it might be helpful here to go ahead and FOIL out the bottom at this stage, because that'll make the bottom a little easier to differentiate when we need that as a part of our quotient rule. So that is x to the 4 minus 2x squared plus 1. This is the thing we are differentiating. And according to the quotient rule, This is the bottom times the derivative of the top. So that's x to the 4 minus 2x squared plus 1 times the derivative of the top, which is just negative 4, minus the top, which is negative 4x, times the derivative of the bottom, which is 4x cubed, minus 4x plus 0. So that's all that she wrote there. And then downstairs we have the bottom squared, which is x to the 4 minus 2x squared plus 1 all squared. Let's distribute things out and clean them up. Negative 4 times x to the 4 is negative 4x to the 4, and then negative 4 times negative 2x squared is positive 8x squared. Negative 4 times 1 is negative 4. And then over here, I'll have minus, and I'm going to distribute this negative 4x first. Negative 4x times positive 4x cubed is negative 16x to the 4. Negative 4x times positive 4 times negative 4x is positive 16x squared. And then downstairs here, I still have this piece. So when I distribute this negative, I'll have negative 4x to the 4 minus negative 16x to the 4. That's negative 4x to the 4 plus 16x to the 4, which is going to be 12x to the 4. I have plus 8x squared here. And then I'll have minus 16x squared here. So that's minus 8x squared. And then I have a minus 4 here, and I have no constant terms here, so I just have this minus 4. And downstairs is just the x to the 4 minus 2x squared plus 1 quantity squared. And in order to find the places where f double prime can change sign, the numbers I need to put on the number line for f double prime, I need to factor this top. And that's a little bit tricky. We can start by bringing out a factor of 4. The bottom, I know how to factor. So here, let's do this. If I bring out the 4, then I'll have 3x to the 4 minus 2x squared minus 1. Yeah, and then downstairs here, we know where this is. This is actually the same thing that we FOILed out before, right? So this guy is x squared minus 1. Let's see. Squared. Yeah. So this is x squared minus 1 squared all squared. Now the trick is to factor this thing. Any ideas how we can factor this? Hamlet. Think about making a little substitution. U equals x squared. Then this would become 3u squared minus 2u minus 1. Right? X to the 4 would be u squared, and x squared would be u. Yeah, I think Trevor's got it right there. So if I use the AC method on this, I multiply A and C. That's 3 times negative 1. That's negative 3. I need two numbers that multiply to negative 3 and add up to negative 2. Those are negative 3 and positive 1. So I write this as 3u squared minus 3u plus 1u minus 1. And then I can factor by grouping. This is 3u times u minus 1 plus 1 times u minus 1. So that's 3u plus 1 times u minus 1. And u was x squared. So this is 4 times 3x squared plus 1 times x squared minus 1. All over, if you take x squared minus 1 squared and raise that to the power of 2, you get x squared minus 1 all to the 4. If we could have made this last step a little bit easier on ourselves if we were willing to differentiate from here. If we differentiated from here rather than foiling this out, then we would have seen the x squared minus 1 factor come out right away. But we would have had to use the chain rule when we took this second derivative. So it's up to you. Do you want to do more algebra or do you want to do more calculus? If you're willing to use the chain rule together with the quotient rule here, then you won't have to do this factoring at the end. So it's a give and a take here. So my critical numbers for f primed, the places where f double primed is equal to 0, or where f double primed is undefined, these will come from setting each of these pieces to 0. Now, before we do that, actually, notice that there's some stuff that can cancel here, right? Let's do that. This is 4 times 3x squared plus 1, all divided by x squared minus 1 cubed, right? This x squared minus 1 can cancel with the factor of x squared minus 1 downstairs. So f double prime will be equal to 0 if 3x squared plus 1 is equal to 0. This actually never happens, right? This is the same as saying 3x squared equals negative 1, or x squared equals negative 1/3. And if you take square roots here, you get x equals I times, say it like this, x equals plus and minus the square root of negative 1/3. These are not real numbers. Right, the square root of a negative is not a real number. It's I, plus or minus I times 1 over the square root of 3. F double primed is undefined when the bottom is 0. So when x squared minus 1 cubed is equal to 0. Take cube roots on both sides and you get x squared minus 1 equals 0. And that's the same as saying x squared equals 1. So x is plus and minus 1 again. So the only thing that's actually interesting here is these guys. Because f double primed is never 0. The only place f primed is equal to 0 is at a non-real complex number. Fabrice, it's an old algebra trick. All the powers here in this thing we're trying to factor are even, right? X to the 4, x squared. There is no x or x cubed. So I just noticed that I have the option to make this substitution, to reduce the powers. So it's an old-fashioned algebra trick that we should have seen both in trig and in pre-calc. But if you haven't seen it before, remind me at the end of class and I can find you a link to a place where you learn this. It's just a trick for solving larger factoring problems where all the powers are even. Because all the powers are even, I knew I could do this. And that's in general what we look for. So if you're trying to factor some big polynomial where all the powers are even, you can make this substitution to turn it into a polynomial of degree half, whatever the original was. So finally, I'm ready to make my number line for f double primed. Only things of interest here are -1 and +1. To the left of -1, I could test x equals -2. If I plug -2 in here, f double primed of -2 is going to be 4 times whatever. Negative 2 squared is positive 4. 4 times 3 is 12. 12 plus 1 is 13. 13 times 4 is positive. So the top is definitely positive. I'll just write it as 4 times 13. And the bottom here is negative 2 squared is 4, minus 1 is 3. 3 cubed is 27. In particular, this is positive. Between negative 1 and 1, I could test x equals 0. F double primed of 0 is 4 times, parentheses, 3 times 0 squared plus 1. That's 4 times 1. The top here is 4. And downstairs, I have 0 squared minus 1, which is negative 1 cubed. Negative 1 cubed is negative 1. So this is definitely negative. And to the right of 1, I could test x equals 2. And over here, if you plug in 2, this top is definitely going to be positive. In fact, it's going to be the same thing we had over there. 2 squared is 4. 4 times 3 is 12. 12 plus 1 is 13. So it's 4 times 13 again. And downstairs here, 2 squared is 4. 4 minus 1 is 3. 3 cubed is 27. In particular, it's positive. So F is concave up. From negative infinity up to negative 1. F is concave down from negative 1 to 1. And F is concave up from 1 to infinity. Now I'm going to take all this stuff together and put it into one thing, one number line. So look here. Try to line these up. They don't quite line up. But we know that F is concave up from negative infinity to negative 1. And we know it's increasing there. That's what I mean. I'm going to take all of this and put it into a number line for the shape of F. So on this last number line, I'm going to put all of the numbers on any of the previous number lines. We've got negative 1, 0, and 1. From negative infinity to negative 1, I was increasing and concave up. So that means that looks like this, right? Remember those graph shapes? Increasing, concave up. From negative 1 to 0, I was, let's see, increasing, concave down. So increasing but concave down, that looks like this. From 0 to 1, I was decreasing and still concave down. Looks like this. And from 1 to infinity, I was decreasing, concave up. That looks like this. So now we're ready to draw our graph. We know we have a local max here at the point 0, 0. We know we have vertical asymptotes here at +1 and -1. And the other thing that we knew we haven't written down here is the horizontal asymptote, which was y equals 2. So here comes our graph. All right, this, I would put all of this under H. All right, I want to mark -1 over here. Maybe like here. And draw in my vertical asymptote. Mark +1 over here. Draw in my vertical asymptote. And I know I have a horizontal asymptote, that's the line y equals 2. I want to mark that and draw it in here. Doesn't have to be perfect, but as good as you can. I know the point 0, 0 is on my graph, so I'm going to go ahead and add in any points that I know for sure. And now I'm going to see what I can do. I know that I am increasing and concave down between -1 and 0, and decreasing concave down from 0 to 1. So that tells me that I have to approach this max like this. And run away from it like this. And since I know that these are vertical asymptotes, that tells me how I approach those vertical asymptotes, right? It tells me I can't be going up here. I'm increasing up to this max and decreasing away from this max. Everybody with me? Okay, what about over here in this region? Well, I know everywhere in this region, I should be increasing concave up, right? Look at this shape. That means I have to be approaching this horizontal asymptote like this here, and this vertical asymptote like this here. And similarly over here, I know I have to be decreasing concave up. So that means I have to be looking like this. Also, we know that we have y-axis symmetry. So if it looks like this over here, it's gotta look like this over here. And there's your graph. This is the graph y equals f of x. And you see, I didn't have to make a big ass table. I only actually know one point on the graph. But from the information I get through the derivatives, I'm able to get a really beautiful picture of this graph. Now, if you want to make this better, you can plug in some x values like -2 and +2 and find what the actual values are on the graph up here. The rule I tell my kids, I want 3 points, minimum of 3 points on the graph. So let's go ahead and find f of -2. Let's find f of +2. F of -2 is, what was this function? 2 times x squared. So that's 2 times -2 squared over x squared minus 1. So that's -2 squared minus 1. -2 squared is 4 times 2 is 8. And then downstairs here, this is 4 minus 1 is 3. So the point up here, the y value is 8/3. This is -2, 8/3. And then by symmetry, the point over here has to be +2, 8/3. So on a test, this would be full credit, 100%, 10 out of 10. I know this is a long procedure. I know it's not a simple thing. If we wanted to be very careful here, we'd say by symmetry, f of +2 is the same as f of -2, which we just calculated. We know that's 8/3. That's where that other piece is coming from. We should label our asymptotes. Here, this is a horizontal asymptote. Its line is y equals 2. These are vertical asymptotes. VA x equals -1. VA x equals +1. It's okay, Hamlet. So this is about as nice a graph as I could possibly hope to have for this function. And if we compare this to what Desmos gets us, I bet it's pretty fucking good. Yeah. Not bad at all. We can add in the asymptotes. There it is, right? Nice graph. So this is what we're after. That's what we went through all that trouble for. This is a pretty complicated function. It's not a simple graph. The big steps here were the number lines for f primed and the number lines for f double primed. Those were the two big things here. The other work is stuff that you should be pretty good at doing quickly. Those are things that we've seen in algebra classes. So I went through them very, very carefully. But with a little bit of practice, you should remember doing that stuff in your pre-calculus classes, and it should go quickly. Questions on this one? All right. I don't think I have time to grind through another one of these. We went through that very, very carefully, and I think we are actually about out of time for the class, right? I would like to do at least one more example, and I'll do that with you guys on Wednesday. What I would like you guys to do is to try, well, I'll just put it in the homework, yeah. So take a stab at the homework problems. I'm gonna pop open a new homework for you guys today. It will have problems like these. I'm gonna tell you now, your test will have one of these. Your test will have a problem like this, right? Where not this function exactly, but where I need you to make the number line for f prime and f double prime, find where we're concave up, concave down, and use that to draw a graph. It won't be as involved as this, but it will be this type of thing. All right. Any burning questions for me before I let you guys go for the day?
Yeah, sorry. Will you be holding office hours through spring break?
That's a good question. I don't really have a plan for that yet. If you want them, let me know. I don't have any plans to travel or anything, so I'll be around. But I might be busy doing like chores and stuff. But yeah, if you guys want an office hour over spring break, I can at least make one happen, I'm sure.
Yeah, if you could, that'd be awesome.
Yeah.
Okay. Yeah, if you think you might want to hour over spring break, send me an email letting me know, or Candice message letting me know which day or days, and I'll make sure to do at least one.
Thank you.
Alrighty, guys. Have a good rest of your morning. I'll go ahead and open up that new homework for you. I did grant all the extension requests that were in there from last week, so I'll knock out last week's homework first, and then take a stab at one of these problems before class on Wednesday. There will be a handful of them in there. Bye, guys. Oh, yep, sorry. What is this? Oh, of course. Yeah, okay. Oh, and Fabrice asks, is this the only way we can find the graph? This is the best way to find the graph. No, you can find the graph by just plotting a shitload of points, right? Make a massive table. That will work also. But if you want a graph that has the right shape and doesn't require spending 5 hours making a table with 1,001 points, then this is the only way. So this is the skill I need you guys to practice. All right, I'm gonna head out. Take care, guys.